Hi, my name is Dylan, and this is my presentation titled Adaptive Sampling for Fishery Stocks in the Eastern Bering Sea. Fishery surveys in the Eastern Bering Sea are bottom trawl surveys that trawl at numerous locations to get a population estimate. The sampling method we currently use is systematic sampling, which is essentially a fixed grid over the ecosystem with a bunch of fixed points that all get sampled during a survey. However, surveys are starting to change in the Eastern Bering Sea, and this is because the ocean is experiencing some drastic changes in sea ice and ocean temperature. These changes are leading fish to move further north and beyond their historical ranges. So our sampling area must also expand to encompass these ranges. However, as I just described, systematic sampling is very high effort, so it makes expanding our sampling a little bit of a daunting task. One thing that we know about this ecosystem is that cold pool extent is a driver of fish distribution. And what cold pool is it's a body of water near the sea floor that's below 2 degrees Celsius. And it essentially acts like a barrier, especially for groundfish populations. So the thought process is, since it acts as a barrier, we can use the cold pool extent as an indicator of fish distribution. And by doing so, we can more accurately assign sampling points to capture the true population. So to explain this in a little bit more detail, let's say that the cold pool looks like this blob here. It's very small. Fish have a lot of room to move further north into some newer ranges. If we see a cold pool like this, we can assign more points into the north to make sure that we're catching those fish moving further up. If in a year we have a cold pool that looks more like this big blue blob, we know that fish can't move as far north, so we would keep our sampling pressure concentrated in the south and feel pretty confident that we're capturing the true population. And what I just described is an example of adaptive sampling. So for my research question, I wanted to see how a sampling method like the one I just described would perform against some environmental scenarios. And I'll explain more about those environmental scenarios in a little bit. I did my research as a part of an internship with NOAA Fisheries. We modeled some adaptive sampling methods, and we guided point allocation using either the cold pool extent or the sea ice extent. We had a 3 operating model system, and you can think of the operating model as the true state of the ecosystem. We had one where fish were entirely concentrated in the south, one where fish were beginning to move up into the north, and one where fish were almost evenly split between the 2 strata and had essentially moved into their new ranges. And the operating model was chosen by the cold pool extent score that was chosen in a run. So let's get into these environmental scenarios and parameters that we tested across. We have 2 here. We have true population density gradient and spatial correlation. So I'm going to start on the density gradient. Essentially, what is going on here is that there is an underlying density gradient that looks exactly like this one here. And what the true population density gradient is a parameter that tells our simulated data how closely to follow that underlying density gradient. So let's look over to the left here. The parameter here is set extremely low, and our simulated fish data, and you can see yellow means more fish, is very spread out. There's no pattern. Our fish are moving up into the north. But when we tell our data to follow that underlying density gradient exactly, we get a very strict gradient like this. All the fish are concentrated in the south, and then they move up into the north across that gradient. And what spatial correlation is the likelihood that fish will be near one another. So when spatial correlation is low, we see a lot of this patchiness here. And when spatial correlation is high, we're seeing these big clumps. All right. And so I tested a number of different sampling methods, but I'm going to highlight 3 for you. We have adaptive stratified, and this is an adaptive method in which the point allocation is guided by sea ice extent. We have adaptive stratified perfect, in which the point allocation is guided by the cold pool extent. And then we have proportional stratified, in which the points are evenly split between the north and the south, pretty much regardless of any environmental indicators. And then we have some error graphs here. So we can see for the true population density gradient, that when our data does not follow that underlying gradient at all, we're getting a lot of error. And then it kind of gradually subsides as we get closer, as our data gets closer to the underlying density gradient. And on the right here, we have spatial correlation. You can see that there is really no trend at all. These are all straight lines. We can say that spatial correlation is having no effect. And one thing that I want to point out is that proportional stratified sampling, this blue line here, is outperforming both of our adaptive sampling methods for both parameters. So that's pretty interesting. What does that mean? It means that we need to try some different things. So some things that we could try to see if our results are affected is we could try to simulate our data from a different distribution family. We could mess with the proportions of sampling between north and south for our adaptive sampling methods. And that's just to say that instead of putting 90% of the samples here and 10% here, we could put 80% here and 20% here instead and see if that has an effect. And we could also just mess with the levels of our different environmental parameters. And that would be if we just increased all of our population density gradient values to see if that has an effect. Essentially, what we have here is we have a model that's creating data, but there's a lot of areas where it could be performing better. We have a lot of persistent bias across our results, and we're also seeing some trends that we did not expect in proportional sampling performing better. So we could try to change some different things in the model and see if we could get different results. And more of a fisheries management implication is that we could research the data continuity implications of changing sampling regimes. And this is just to say that we've been sampling the same way in this area for a long time. Would there be any challenges of switching to a new system? So my main takeaway, I just want to reiterate that adaptive sampling could be a great way to expand our sampling area without overusing effort in years where fish aren't in those new ranges. But it needs to be tested a little bit more, and we need to see if we can reduce some of the error in these graphs and get some trends that we're more expecting to see, which would be our two adaptive sampling strategies performing better than proportional sampling. And I just want to zoom in on this image here so you can see what a bottom trawl survey looks like. They are counting fish and they're having a great time probably. And for people who are interested in this kind of stuff, this is what our data looks like. We have a data frame of parameters here that we looped through during our simulation. And then we have a data frame, and this is actually our results. So you can see all of our parameters, cold pool scores, ice values, estimates, and truth. And those are both abundance measurements. And then the sampling strategy we used. Are there any questions?